Well, thank you for the introduction, Katie. So I'm actually a postdoc at the museum working with Richard Harrington and Robin Armstrong. And I'm going to talk today about Ben Williamson's study on plagioclase, about whether it can be used as a fertile discriminator, fertile barren discriminator, in porphyry systems. Just before I kick off, I'd like to acknowledge our colleagues from the Akita University in Japan, who helped us out with our fieldwork earlier this year. So this is just an outline of what I'm going to talk today about. So the plagioclase discriminator introduction, so I'll talk about what Ben suggested in his study a year ago. And then this kind of ties in with some of the other research that's going on at the Load Group in the museum with using minerals as possible vectoring tools for porphyry fertility. I'll then speak about the mineral resources of Japan and show a map, and so basically why we're interested in looking at Japan. And I'll then talk about the GEOROC database and how we use that as a kind of use to identify potential sites for sampling in Japan. I should say that I don't actually have the data yet from Japan. I'm still waiting for a couple of months to use the probe. So what I'm basically going to be talking about today is the fieldwork itself. So we've already today seen lots of images about porphyry systems, so I'm just going to kick straight off into Ben's original study. So this is a graph showing plagioclase compositions from two separate areas. This was his kind of case study. So on the x-axis over there, they have the aluminium versus the alkaline ratio in plagioclase, and on the the x-axis we have a northite content. And it's also willing to point the error in these values as well, which will be shown later as well. So what this basically shows is that if you look at the perfect plagioclase composition, which is that red line shown there from albite up to the northite, it shows that there's a discrepancy in between plagioclase compositions that are associated with mineralization and those that aren't associated with this with mineralization within this case study. And then if you move that on to have a look at some of the data from the literature, so these are all data points from calc-alkaline rocks, magnetite series granitoids. So some of these fertile field areas, so these include El Teniente and Bingham Canyon. You can see that there's a difference between the compositions of those compared to barren field. And this composition comes about because of the theoretical aluminium composition within the plagioclase is higher in the fertile areas than it is in the barren fields. And so Ben stipulated for a couple of causes of this potential excess aluminium. So this is to do with the non-conventional substitution. So basically what happens is that aluminium substitutes into the large cation site that's normally occupied by calcium or sodium. And this is likely to be due to H2O content. And then he stipulated that this might have potential implications for any copper uptake within the crystal lattice, but that remains whether we're going to have a look at that further for sure. So then this moves on to our planning for the mineral resources in Japan. So this is part of our planning for our fieldwork. So what I've done here is taken the data from the Geological Survey of Japan and divided it up into different deposit types. There's a gneisel and skarns there, a few magmatic deposits, so that includes kind of nickel and PGEs, and some sedimentary hosted mineralization, and then these stratiform deposits, so these up here and in the south over here. So the north ones are the Kuroko-related deposits, and the south ones are kind of the Beshi-type deposits. But these are formed in extensional environments, and they're grouped together specifically to show this, that they actually do have quite a large occurrence in Japan. And then there's also a few skarns and then hydrothermal systems. So these hydrothermal things are vein deposits, so this is including epithermal deposits and intrusion-related deposits. So that's the whole kind of range of veins. But as you can see, there are no porphyry deposits on there, and only very few kind of porphyry-style or porphyry-related mineralizations. So this has been proposed to be down to extensional environments, which lead to more kind of Kuroko-type or Beshi-type deposits, which is kind of counterintuitive to form porphyry coppers. Possibly that we're at the wrong level of exposure and that these systems haven't been eroded down, or they've already been eroded away, so we're not actually seeing them close to the surface. Also the potential for volatile escape from magmas, so that the copper and the base metals are already lost before we actually form a deposit. Other stipulations include that copper has already gone, and in that it was never, originally there to begin with, so it's actually a low copper abundance in the magmas themselves. Also that there's the potential that it's a relatively reducing environment, and that a lot of the granitoid series in Japan are actually ilmenite and not magnetite series. And then also it's thought that it might be due to an absence of thicker crust, which restricts the amount of fractionation and differentiation that can occur. So this then leads us on to processing the GEOROC data for Japan to identify new sites for sampling. And we were going to use this as a barren analogue to compare to other data from the literature and possibly some other fertile sites. So this has undergone quite a lot of kind of data tidying up. So anything that had bad totals, bad oxide totals, was scrapped. And then once the APFU for Plagioclase was calculated, this was then removed. And as you can see, the compositions for Japan Plagioclase and Japan, the metaluminous rocks, Plagioclase, these majority of them plot below the line, so in the barren field for Ben's Plagioclase discriminator, and it's far more barren than other data points from the world database. So if you then move on to just show some simple box and whisker plots, so if you can see worldwide, as you would expect, this actually plots in the median and the mean plot in the barren section, as you'd expect, because porphyry environments actually forming a deposit is actually atypical, so you would kind of expect that. But then Japan and the other Japan compositions are kind of a lot lower, as in they're a lot lower than the average. And then we've also included some data from the Western Luzon arc as well as a comparison. So this then predicates, our investigation, and then so where are we going to do that? So we've plotted this up spatially. So on the left-hand side is the excess aluminium for Japan. And this shows that, I also note the scale as well. So earlier we saw with the deposits from the case study in Chile that the excess aluminium was kind of 0.3 to 0.4, but even when we're seeing an excess aluminium in the Japan samples, it's not that high anyway. So there are various areas where it's slightly elevated, but most areas it's actually quite low. And then this is in comparison to the strontium over yttrium ratio, and as that's been discussed yesterday and earlier today, this can be a useful analogue to show the water content of the magmas, which, as we know, is required to form porphyry. So from this data, we identified 4 specific areas. So the first one is the Nagasaki and Saga areas. So this shows moderate excess aluminium plagioclase, kind of clustered around, but low overall whole rock strontium and yttrium. The other area was the Shimane prefecture, so this shows excess aluminium in plagioclase and also some areas of high whole rock strontium yttrium. The third area was the Hida Mountains, so a few associated molybdenum deposits. It also shows excess aluminium in plagioclase, but then some high areas of strontium yttrium. But then the deposit the area that we actually settled on was the Kitakami Mountains, which is area 4 on the map. So this is a series of magnetite series granitoids, which has high strontium yttrium, but interestingly, there's no plagioclase data for this region, so this is one of the reasons, this is the main reason why we want to go there. But they also show gold quartz veins and copper iron skarns, so there is some mineralization within this area, and wanted to see if you can pick this up in the plagioclase signature. So this is our kind of localities of where we visited. So the Osarizan field is a Quaternary age field that's mainly dacite in composition, but it's active at the moment, precipitating high levels of gold and arsenic as well at the moment. The Osarizawa site is a closed mine, but this was a kind of polymetallic site where they extracted mainly copper and gold within quartz veins. So I think this is kind of an intrusion-related deposit. The Yakiyama volcano is an active shield volcano that's made primarily of andesite. But around there was some hydrothermal activity, and we saw in some areas some argillic alteration. And also this has a history of phreatic eruptions, which have actually brought up a class of kaolinite and other associated clays that you'd expect to see in argillic alteration. So then the Taihizan, Tono, and Miyaku areas, these are all Cretaceous granites or granitoids, variable strontium over yttrium ratio, so we're going to use these as a comparison to each other, basically. And then finally, the Kamaishi deposit is a large copper iron skarn. This is the largest skarn deposit that's in Japan. This was Cretaceous age Ganadaki igneous complex was intruded into some Permian limestones and formed an enormous skarn deposit of kind of with 14 or 15 different ore bodies in that area. And historically that's been mined for quite a long time, but now it's shut down in the 70s. So basically with those samples, what we're going to do is plot them up, get some whole rock data, get some Plagioclase data to calculate the excess aluminium, and then we're going to be comparing this to the literature, so other sites like the GEOROC database, and then some other fertile systems. So we're always looking for material to work with, especially to use as a comparison and get some new data. And what we'd like to do with this is, if it turns out that this can actually be used as a potential discriminator, then apply it to kind of exploration in industrial areas to see if we can find any porphyry copper deposits that haven't been discovered yet. So thank you very much for listening, and are there any questions?
It's got plenty of time for questions, so...
Do you intend to do infrared spectroscopy on your Plagioclase?
We thought about doing that earlier, but I think at the moment it's not going to be. But when the Japan stuff comes back, we are going to try and do it. Yeah.
I suspect one of the possible interpretations of the excess aluminum is hydronium ion, H3O plus 1, substituting in the alkali sites. It does so in hydronium micas, hydronium jarosites, and so forth. Substitutes for potassium in the alkali sites. And in micas, hydronium is distinguishable from neutral water molecules in the alkali site by infrared spectroscopy. So you might be able to distinguish whether or not your excess aluminum is just failure to charge balance with all of the irrelevant cations.
Yeah. Okay. So I'll check that with next time.
Infrared spectroscopy should
Something to bear in mind for the future. Yeah.
So that would be an explanation of the excess aluminium. What about the ones that are deficient in aluminium, the ones that plot under the line?
So
they go both ways.
Yeah. So I mean, a lot of the actual barren areas kind of plot closer towards that actual line. But in terms of our explanation for the barren systems, we're not actually sure of why that is, but it might be down to the water content and kind of the lack of water that's available to form the porphyry deposit.
I don't quite get that. You can't have negative water.
No, as in that lack of it is because the water actually causes kind of a deformation within the lattice and actually causes a difference between the aluminium and the silicate restructuring. So that helps substitute aluminium into the site that it shouldn't normally form into. But the lack of water might just be an indicator that that there is there isn't any water available to form that lattice, so you don't get an excess aluminium signature.
Okay.
So you mentioned something to do with copper substitution into plagioclase.
Yeah, so one of Ben's thoughts as to why you end up with high copper in these systems with water is that it actually restricts a bit of substitution into the plagioclase lattice, but whether or not that's kind of something we want to develop on is another matter, because actually measuring copper in plagioclase can be quite difficult, especially on the laser. But I think what's more important is to highlight the water content in comparison to making it more fertile over the actual copper.
But you're not suggesting that you don't make a deposit because you've wasted all the copper on the plagioclase, are you?
I think that was his original suggestion, but I'm not sure if that's true.